Okay, so new topic for today. We finished triple integrals last time. And by the way, so you'll notice we're going in a different order through chapter 14 than the book does. Kind of a optional, different points of view on how you can approach all these different topics. I think that there's something very nice to be gained by doing change of variables, which is near the end of chapter 14, doing it kind of in the middle so that we can use the ideas that we develop here for several sections kind of near the end of chapter 14. So I think this is a natural starting point. Obviously the authors disagree with me. We whatever. It's their book. But it's my course. So we get to do whatever we want. Everybody wins. So here we go. Change of variables. I'm going to start off with an idea about how you do integrals. Now this is back to single variable calculus. Single variable calculus. And y'all remember that we defined all of this structure here for a single variable integral, and in particular delta x is b minus a over n. Notice when you write delta x equals b minus a over n, implicit in that is that all of these delta x's are the same. This is what we call a regular partition of the interval from a to b. Why did we do it that way? I don't know. Seems like a reasonable choice or something. I know, it's convenient, right? It's very convenient. You got to give me that. But is that really a good reason to make a choice? An arbitrary choice? There's actually a lot to talk about there. So I'm going to make an observation though, and that is that you would expect, and it is usually true, that it wouldn't matter if you did an irregular partition, right? So notice what I've got here. This is not just bad drawing. Those pieces, those intervals in the partition are conspicuously different in size, right? And I've indicated thusly not equal, right? So as long as we would speculate plausibly, as long as as you slice. As n approaches infinity, as you slice more and more, as long as it's true that as you go, the largest remaining piece is getting smaller and smaller and approaching zero, wouldn't it seem reasonable that you would still get the same value in the limit of the Riemann sum, right? Who really cares? If you chop up, if you have a piece of metal like this, and if you chop it into little pieces, and you make the case that the total mass is the sum of the little masses, it doesn't matter if those little pieces of masses are the same length, right? It's still mass is the sum of little mass. Mass is preserved. Mass is an accumulating quantity, completely independent of size. So, turns out that this is usually true. I'm going to say it's true for integrable functions, and let's not. There's a deep dive into exactly what does that mean and exactly why, as a result, is this true. And it's a wonderful discussion. And every year when I get to this point in the class, I start going through. Oh, here's how I'll get that done in 45 seconds, really. But no, it's a long conversation. But it's a lovely long conversation that I always kind of have to resist talking about. If you're interested in that sort of thing, then you should take Math 431, which is not as hard as it sounds, but it's a very fun course, and it explores a bunch of ideas a lot like this. It's really, really interesting stuff. Classical math stuff. Okay, as far as we're concerned in Math 212, doesn't matter. Okay, so why do we care? Why would you ever want to do an irregular partition? Right? But it's so much easier to just say, let's just do a regular partition. Delta x is b minus a over n. We got a formula we can plug in. It seems like it would just be notationally awkward to do it in an irregular way. Well, that argument presupposes that we are interested in actually cranking out numerically a Riemann sum, right? And you just got to remember that that's not what we're doing in this class, right? We're not actually cranking out numbers. I mean, sometimes we are, sure, right? But for Riemann sums, we're not actually cranking out numerically Riemann sums. So the question is not which is more convenient numerically. The question is what's more convenient conceptually, right? And having an arbitrary restriction for no particular reason that we can really justify that, oh yeah, these pieces have to be the same size. If they're not the same size, then I don't know what you're talking about, right? That's an arbitrary restriction. Why are we tying our own hands in this way? That is less convenient, and allowing yourself the freedom to make your partitions non-regular, as long as the pieces are approaching 0 in size. Much more convenient. It gives you more flexibility, and we're going to capitalize on that flexibility pretty much right now. Okay, so I want to another flashback to single variable calculus. Y'all remember the substitution rule, right? Ancient history. Does everybody remember this? This is just how you write down the substitution rule, but the big idea is that du is g prime of x dx, right? So that implies that. And it's kind of notationally pretty satisfying. And, from a notational point of view, this is pretty easy to swallow. Y'all might have seen a proof of this fact, though, a little bit more rigorous. You can prove this from the chain rule. And again, I've hit this button with my elbow. Sorry. Oh, man. They should put like a little lid over this thing so you can't do that. You can use the chain rule and, cleverly applied just so to actually prove this, independent of, sort of notational games. I'm going to show you a different point of view on the substitution rule that is important to make a generalization. And again, as we often do in this class, right? We're going to take an idea from Calc 1 and we're going to say, okay, that worked great in Calc 1. What can we do with that in a multivariable context? All right, so let's revisit this substitution rule for integrals from a as a Calc 1 concept, but in a way that's going to generalize. Okay. By the way, don't forget when you do the substitution rule for integrals, these bounds don't just automatically turn into the same bounds, right? You notice those bounds change. And one way to think about that, if only sort of for kind of, memory, is that when x is equal to a, for example, well, just stick that in there. If x is equal to a, notice that tells me that u should be g of a. Right? I mean, that's just downright plausible. Right? That makes sense to everybody? Okay. All right. So I'm going to try to give you a better reason. Okay, so here we go. The idea is to take this formula and view this formula, u equals g of x, less as sort of an algebraic sort of trick, algebraic games, an algebraic foot into a symbolic manipulation game. And let's view it a little bit more sort of literally as, u is the output value, x is the input value, and we're going to actually draw such a function, right? U is g of x. Let's draw the x-axis and the resulting u-axis. And notice, this point A, when you put it into G, is going to come out as G of A. And this point B, when you put it into G, is going to come out as G of B. Right? Okay, that's just observation. Now, I'm going to put a partition on this interval from A to B. And by the way, feel free to make it a regular partition. I don't care. Doesn't matter. Per the previous page's discussion. There's a partition on this interval from A to B. And, all of these values will just plug right into that G function as well. And out comes a bunch of values that are probably not regularly spaced. And again, I don't care, right? Per the discussion on the previous page, whatever, as long as the size of the largest piece in the partition is approaching 0, doesn't matter. Okay, all right. So that's just an observation. Now, what that has to do with integrals, we'll come to momentarily. Another idea, as relates to this, we can call these little distances here, like I can call that. Delta U. Well, now I better not just call it delta U by itself. These delta U's are all different. This is an irregular partition. Let me call it delta U sub 1 because it's it's representing the size of the first subinterval, right? Likewise for all the rest of these pieces. And let's ask, how does the size of delta U compare to delta X? Right? We start with some little object of some size in the domain that gets turned into an object of some size in the target, how much does this size increase by way of the action of this function, right? Or said differently, how big is the stretching factor, what I and others like to call the stretching factor? I mean, we don't think of functions in this way most of the time. Most of the time we think of points go in and points come out. Points have no size, right? So a point goes in, a point comes out, something of size 0 goes in, something of size 0 comes out. There's no notion of stretch. But if you put an entire interval in, all the points, right? You get an entire interval out, there is this idea of how do those sizes compare. And that's going to be something we're going to be interested in going forward. And again, we'll see why momentarily. Well, the easy observation here is that even though I think of this as a size in and a size out, you can just choose to reinterpret this as a change in, right? X changed from that value to that value, and in so doing, U changes from that value to that value, right? And what's the relationship between a change input and a change of the output? That we know, right? The relationship between the change of the input and the change of the output, that relationship, aka the stretching factor in this case, is the derivative. Yeah? Everybody on board so far? Now we're just kind of developing some tools that we're going to use momentarily. So why we're developing these tools, perhaps a little ambiguous still, but that's all coming. But is everybody on board with these observations? Everybody's good. Okay. We're going to use this notion of stretching factor a bunch in this course. So anyway, I like to start with the single variable version of the book. Doesn't do any of this stuff, by the way, but I think this is good for sort of context to kind of get us get the groundwork laid on which we can build how this is going to show up in future contexts. Okay. All right. So all of that having been done, let's consider our situation here. Again, we have an interval on the x-axis, a resulting interval on the u-axis. And, oh, by the way, in one of these x subintervals, I can talk about the sample value, xi star. Well, that being a value of x, you can plug into the function and out comes the sample value of u in the corresponding interval on the u-axis. No surprise, I'm going to call that ui star. Okay, all right. Okay, so this observation is that. The observation about how delta x relates to delta u is that. Right, input size, output size. Talking about all that. And turns out that this is all we need right here. This right here is all we need to turn an integral on the u-axis into an integral on the x-axis. This is just kind of an algebraic observation, but here we go. Notice that all of the stuff over, well, here, let me write it like this. Every object in this u integral, note I have an integral from u0 to u1. This is an integral on the u-axis, right? Everything in that expression I can rewrite in terms of x's. So, for example, this ui star, that's g of xi star. We just talked about that. Right? That's the fact that this point goes to that point. Yeah, let's plug it in. And then likewise, delta u, we just talked about, that's g prime delta x. This piece gets stretched out per the derivative to turn into that piece. And lo and behold, as a result of these two observations, note that this entire expression here has been rewritten as that expression. Who cares? Well, because by moving some parentheses around, this expression is an integral on the x-axis. Right? So making these observations about what the function g does in turning the purple interval into the blue interval allows us to rewrite an integral on the u-axis into an integral on the x-axis. Everything in that blue expression for the integral on the u-axis, rewrite in terms of x. Okay. All right. So just a little bit of terminology. This is what we call a pullback. I'm going to try to explain why we call this a pullback. It comes from just sort of reinterpreting what the function g is doing here. We normally think of a function g. Notice how we even draw the function g. We draw the function g as going this way because that's what g does. G takes stuff from the left and gives you stuff on the right. Well, now let's be more precise. It takes points on the x-axis and gives you points on the u-axis. And so in that sense, this is going to the right. G is going to the right. What we're doing here is reinterpreting g in terms of what does it do to algebraic expressions. To algebraic expressions, this is just how plugging in works. It's a weird thought, but this is how plugging in works. An expression involving u, if you then just plug in u as g of x, that expression involving u turns into an expression involving x. It's in terms of what it does to expressions, g goes the other way. Everybody see how that happened? Again, I assert this is just how plugging in works. Right? This doesn't even have to be a calculus observation. This could be an observation about just expressions, any expression involving variables. Right? So, thus the name pullback. Common terminology. I'll be using pullback a lot in this class. I'll probably be abusing it slightly. Let's not worry about that. I think it's a very reasonable choice of term here. So this is called a pullback. An integral on the u-axis we rewrite as an integral on the x-axis, and then you recognize that what we've shown here then is exactly the substitution rule. All right, so this is a point of view that, again, you probably have not seen on the substitution rule, but it's very, very valuable for context here in a multivariable course. So let me take a pause here. Is everybody on board? See how this works? And it's just a matter of observing that a function that pushes to the right pulls expressions back to the left. Okay. All right. Okay, so as we always do, let's see how we can use this single variable idea in a multivariable context. Right? So let's suppose we have some domain in the UV plane. And let's suppose I have a function called g that pushes forward into the xy plane. Now, what's the image of this rectangle going to look like? Well, g doesn't have to be a nice function. G could be all curvy and twisty and weird. In which case, the image of that domain might be curvy and weird. Yeah. Okay. Well, very analogously, if I think of, let's say, a point here, u comma v, and if I think of that as being, if I plug into g, then that gives this output x comma y. Right, so g of u comma v gives me x comma y. All right, well, plugging that in allows me to turn an expression involving x's and y's into an expression involving u's and v's. And note, again, we have a pullback situation. Right, I can take an integral defined on the output domain, and I can pull that back to an integral defined on the input domain. Same strategy. Okay. Now, I did kind of gloss over a pretty important detail, and that is what's the relationship between these sizes, right? This little size, the size of that little piece there, and the size of this little piece here. Well, who says they're the same, right? They weren't the same in the single variable context, right? There was a stretching factor by which this little piece gets stretched out into this much larger piece, perhaps. Right, so what's the form of that here? Well, that's a good question, right? How much bigger is this stretched out into? And so I'm going to recognize that by rewriting area dx dy as area du dv times the stretching factor. And we don't know as of this moment what that stretching factor is. Now, since there's enough going on in this discussion at the moment anyway, I'm going to not derive that stretching factor for you here. I'm just going to tell you what it is, and you can take my word for it. And then we're going to I'm going to motivate it a little bit later. I mean, we're going to have some further discussions of this idea of a pullback in which it's a little bit easier to kind of get our hands on. So for the moment, I'm just going to make the following assertion, that this stretching factor is computed by that formula. Specifically now, notice this algebraic list of equivalences. This thing, now the determinant of the Jacobian, y'all know what determinant is. Y'all know what the Jacobian is, right? So the determinant of the Jacobian is a thing, right? So here we go. That is just that. And then a very convenient notational choice is to rewrite this as what appears to be a fraction. It's kind of a weird looking fraction, but partial xy over partial uv, very convenient, and I'll show you why in just a moment. But that we're going to use that notation a lot. Partial xy over partial uv means the determinant of the Jacobian of the function that views x and y as as partials of u and v, in terms of u and v. Okay, so notational choice. So the absolute value of that Jacobian determinant is the stretching factor. So you can just take my word for that for the moment. Let's see here, did I finally put this whole thing together? No, I guess I didn't. So anyway, this formula for the stretching factor goes in there. Okay, is everybody on board? Yep.
How do you get from the determinant of the Jacobian to that
Oh,
formula?
yeah. So this is just an observation of that the Jacobian matrix. The Jacobian matrix is this matrix, right? So remember that from chapter 13. If you view a function that has several input variables with several output variables, then there's this matrix called the Jacobian that takes input velocities and gives you output velocities. So we talked about that a long time. It was a long time ago, to be fair. Yeah. Is that you remember that discussion? Yeah.
How do you get from the big blue circles like the one on the right?
Oh! This is just a notational choice. Okay. You want to see why? Yeah. No, I should have discussed that. Okay, so let me take this and plug it in into this formula, and here's what we get. So integral f of g of uv. Now I'm going to plug in, per your request, the stretching factor is let me do it like this. Stretching factor is the absolute value of this notation that you're asking about. All right, so let me write that down. Absolute value, partial xy, that's an x, partial uv. There's my stretching factor. Let's see here. dA, now the dA, let me write that as du dv, equals integral over g of d, f of xy, dx dy. Right, so that's what this formula here just turns into by way of plugging in that thing you're asking about, right? And now you can see why this is convenient. Again, it's just a notational choice, right? But then this is that, which looks like those just canceled. So it's a very satisfying, it's notationally satisfying, it's symbolically satisfying notation. That's why we use it. Does that make sense? Okay, so that's our motivation for using the notation. But in terms of definition, it is what it is. This expression is that, which is that Jacobian determinant. Okay. Now I do have to point out one other little eye-rolling annoyance. This also just a notational choice. Nobody's right, nobody's wrong on this. The book prefers to use JG to refer to what I would call the determinant of JG. To me, J is a matrix. The Jacobian is a matrix. That's how we've used it in the past. It's a matrix. It's something you multiply by a vector to give you another vector. The book is using JG not to refer to the matrix, but to refer to the determinant of that matrix. That gives them one less thing to write down. Okay, that's true. But then they can't use J as a matrix that multiplies by vectors to give vectors. So anyway, just heads up, that's how it's a notational choice. It doesn't really matter. But I encourage you to use my choice here. No one will not know what you mean if you write it my way. And there's a question if you write it the book's way. Anyway. All right. So let's see an example. Let's compute this integral here. That's an integral you'll notice in the xy plane. Now, specifically, my domain, R, is the image of the unit square by way of this wacky function there. Right? It's the image of the unit square, and the unit square is over here. All right, so we have an integral that's defined on this green domain. And this green domain is defined as the image of a nicer domain in yellow. And the question is, can I rewrite the integral on the green domain? Can we rewrite that as an integral on the yellow domain? Everybody on board? We're just going to straight up apply these ideas here, right? We're going to do a pullback where we turn that integral into that integral. And notice the process is it's very plug-in. It's pull back, plug in what you know about the values of the variables, plug in these stretched out domains, and everything else is just a matter of kind of simplifying. I mean, it's very pluggy-chuggy. So let's do it. Now, in order to do this, we do have to take our g function, and we've got to compute its Jacobian determinant. Right? So there's our stretching factor. Going to have to take this matrix. I forgot to write determinant. Shame on me. I guess I was in the book notation mindset there. Sorry. So we got to take the determinant of that matrix. Notice this is just the matrix of partial derivatives, just like we did back in chapter 13. Those are easy partial derivatives. Right? So the partials of that give you the first row. The partials of that give you this row. Yeah, everybody remember that? Or alternatively, if you want to think of it a different way, you can think of it as partials with respect to u. Give you the first column, right? And partials with respect to v give you the second column. Same matrix, either way. Just make sure to keep it straight which way you're doing it. This problem here, right? Inadvertent transpose. Got to be very careful about that. Now, not that this will affect the determinant. It doesn't affect the determinant. But errors that don't result in numerically wrong answers at the end are still errors, right? So do be careful. Make sure to write that matrix down in the right order. Okay. All right. So, I didn't mean to erase that part. I need to erase. There we go. Okay. So here's what that ends up being. Now, do be careful with absolute values. You got to worry about this. Absolute values, you can't just throw them away. There's a lot of high schools, mine included, that pretty much if you just kind of ignore absolute values, they're like, yeah, okay, that's whatever, right? But it's a problem. It will give you wrong answers. Your bridge will fall down if you ignore absolute values in the real world, right? So we got to worry about whether this thing in here, of which we are required to correctly find the absolute value, is that thing positive or negative? If it's positive, then yeah, you can throw away the absolute values. But if it's negative, we've got to take a negative of it. Yeah. Okay. Well, which is it? How do you tell? Answer, we already know what U and V are. And here's how we know what U and V are. U and V are told to us right here. Right? I can see from this picture that U is always between 0 and 1. And I can see from this picture that V also always between 0 and 1. Knowing that, if U and V are both between 0 and 1, then 4UV is clearly between 0 and 4. Subtract 9, clearly negative. Yeah? Everybody on board? So, this is not something I have to just kind of hand wave or, try to, kind of cheat my way out of, right? I mean, I know for sure that the absolute value of this is the negative of the thing inside of it. Okay, all right. Right, so now we're down to plug and chugging. So this stretching factor that I just computed here, that stretching factor is what allows me to rewrite dx dy as in terms of u's and v's. Everybody on board? Now then there's the question, what do I do with the x's and y's in the integrand? Answer, don't forget, x and y are g of u comma v. X and y come through change of variables function. They come through g from u and v. So g, this change of variables function, tells you what to plug in for your x and y, and you can see that happening right here in the algebra. I think I can get this all on the page here. This x here, let's see, I'm going to have to zoom out one more notch here. This x is u squared plus 3v. Reading it straight off the change of variables function. Likewise, this y right there, well, y is v squared plus 3u. Everybody see that? Okay. Now everything's in terms of u's and v's, and you're off to the races. Yeah.
So for this final switch integral, the inside-outside, du dv versus dv du, it's fine. You could switch it as long as you switch the bounds.
Yeah, totally fine. Yeah, so this is just an integral in the UV plane, and it's just like any other section 14.3 integral. You can do it whatever order you want, right? Totally. Okay, does everybody see the mechanics of this process? Now let's talk about motivation. Who cares? Right? I've successfully turned one integral into another integral. So, what is this bias? Why are we wasting so much time on this? Is this just mathematician games? Here's the why. Here's the really, really valuable why. We started faced with this challenge of computing an integral over this domain. And that domain is ugly. Right? I mean, let's just let's forget about this whole change of variables thing, and let's what would I do if I had to do an integral over this domain? Well, I guess I'd have to slice it up like I sliced through a corner. Okay, then I keep slicing, and I sliced through a corner again, right? And then I got to keep going. So I'm going to have 3 separate integrals to do there. That domain is highly undesirable. Pulling it back, notice my new domain, rectangle. Everybody's favorite domain for an integral. Right? The bounds are constants. There's no slicing issues. It's the world's easiest domain. So that's the big valuable thing. And this is a contrast, by the way, from the substitution rule. Here's the substitution rule again. Right? Why did we care about this? And of course, you can go the other way too. Why would we care about rewriting one of these in terms of as the other? Really, most of the time in Calc 1, the reason we would do a substitution is because we don't like the integrand. I don't remember how to do an integral. I don't have a memorized formula for how to integrate this integrand. Maybe that's a hard one, right? So I rewrite it as an integral involving this integrand, and maybe that's an easier one, right? Or vice versa. Right? It's all about the integrand. It's all about the anti-differentiation and the bounds. Right? That's just the numbers you plug in at the end. I mean, that's the trivial part. The bounds are not the problem there. The domain is not interesting in the single variable case. In the multivariable version, it's pretty much all about the domains. And the integrands we're much less afraid of, right? I mean, I suppose this is a little bit more annoying. But well worth the trade, because this is 3 integrals. Right? In fact, furthermore, that's not just 3 integrals. Let's think about what one of those integrals would be. One of those integrals would be on this shape here, and I would have to figure out what the equation of that curve is, which I don't really have. Right? I don't have y as a function of x on that curve. I have y as a function of u and v on that curve. I have an algebra problem. I have 3 hard integrals, and I've turned that into one still pretty easy integral. Everybody happy? Okay. It's all about the domain. Okay. So, all right, here's another example. Now, using some linear algebra that y'all haven't seen yet. By the way, we will in Math 216, for those of you who are going to come on to Math 216 next semester. This function executes a rotation counterclockwise around the origin by an angle theta. It just does. For the purposes of Math 212, you can take this as free information. And it's not that hard to show that this is true, but it's not Math 212. So that's free information for the purposes of this course. Now, using that, here's the question that we face. I've got an integral defined on this domain here. Right, that's my integral domain. Which, you could do just for 14.3 style, right? All you have to do is start slicing, right? So you, let's do this in purple. Start there and you slice. Up, hit a corner. Okay, keep going. Up, hit a corner again. And then keep going. So this is 3 integrals. And, the bounds aren't that bad, but it remains. This is still 3 integrals, and that sounds like effort, right? So let's try to outsmart our way around this problem, right? And so this domain we're going to get rid of by making a pullback argument. We're going to view this domain as being an image of a different domain. Now, we were just told that this rotates counterclockwise by an angle theta. So what can I rotate counterclockwise by what angle to give me this yellow square? Well, this is a geometry game, right? And by the way, think strategically. We're looking for a domain that we like here, right? And so let's view this yellow square as being a rotation counterclockwise of that nice, pretty, lined up, convenient blue square. Right? So the angle is just, well, what's that angle? What's that angle there? Everybody on board? And I refer you to your trig that y'all are hopefully all well brushed up on. Just remember, the prerequisites for this course are used a lot. So make sure you're really good at all your values, the standard angle values of the trig functions and all the trig identities and all that. Y'all have seen how they come up a lot already. So anyway, that's just another reminder. So with that being said, question?
That equation rotates it counterclockwise?
It rotates counterclockwise. That's right. Exactly. Which is what we're doing here, right? That we're rotating this square. Here, let me do it like this. We're rotating that square counterclockwise to give us this square. Everybody on board? Okay. We're just viewing this. Square in the UV plane over here. Okay. All right. Okay, so a little bit of trig. You can persuade yourself that angle. This angle is pi over 6. Trig games. Make sure you can do that. So with that value pi over 6 plugged into this formula, this value plugged into there, this turns into that. Again, that's just a little bit of trig. And here's therefore our change of variables function that we're going to use. Once you have your change of variables function, which, by the way, I'll come back and talk in a moment about, how do you find your change of variables function in general, and there's a few things to say there, but we'll come back to that. This is our change of variables function in this case. Once you know your change of variables function, you got to find your stretching factor. There's your formula for your stretching factor. You got to play the game. Don't forget that x, right? That x is just the first coordinate of the change of variables function, and you got to know your y. And y is the second coordinate of the change of variables function. Yeah? Okay. Okay, so crank out on this formula. There's your Jacobian determinant. Multiply, etc. 1. By the way, that's pretty plausible. I think if you think about this just, geometrically, right? I mean, forget about the formulas. We took something and just rotated it. Things don't get bigger when you rotate them, right? Wouldn't that be weird if just the act of rotating something made it bigger? All right, so stretching factor better be 1. That's a sanity check. Okay. By the way, in Math 212, still please do the calculation, even though it's geometrically kind of a freebie. The course is about the understanding how to make use of the formulas, and if we make something that ends up being convenient, that doesn't mean that we are still not interested in the actual computational proficiency. Okay. All right. So anyway, our stretching factor being 1, as we computed there, dx dy is 1 times du dv. Now we still have to plug in for the x's and y's. Well, same game. X. X is still that. Y is still that. Plug it in. Now that's a little bit annoying. You got to take these expressions and square them and add them and collect terms, etc. And it turns out, in a weird, initially seeming weird coincidence, that x squared plus y squared turns into u squared plus v squared. How about that? That is not just I'll just erase the x and put u instead, and erase the y and put v instead. That's absolutely not true. Witness these formulas, right? X is absolutely not just u, and y is absolutely not just v. So don't fall into that trap. So why is it then that this expression turned out so nicely? Well, again, pretty plausible if you think about it. That represents distance from the origin squared. Right? Well, if you rotate something, its distance from the origin doesn't change. So that's actually pretty plausible also. again, for sort of geometrically coincidental reasons, right? That's a sanity check. That's so you can feel better about what happened here. That's not a technique that I want to see on the exams. Okay. All right. And so again, now notice what happened. We had this integral defined on a domain that we didn't like. This domain we don't like because, well, we're hitting corners all over the place, and so that's going to be a hard integral. And we've turned that instead into this integral defined on a rectangle. Again, everyone's favorite domain, and that is much easier to work out. We just saved ourselves 2 integrals. Everybody happy? Okay. And minor victory. In addition to that, is we saved ourselves having to find the equations of all 4 of these lines. Not that that's that hard, but it is 4 times a little bit of inconvenience, and so that's a nice little bit of efficiency as well. Okay, all right. Okay, next example. Oh, okay, so first an observation. Here's how we've been thinking of the change of variables process. We've been thinking of x and y as being functions of u and v, in which case the stretching factor is that little Jacobian determinant that I write as a symbolic fraction. By the way, just a point of order, quick point of order. This really looks like a fraction. As you all know, we've encountered situations like this before. Just because it looks like a fraction doesn't mean it's a fraction, right? Remember change of variables? Chain rule, right? Just because it looks like a fraction doesn't mean it's a fraction. Okay, this is not a fraction. That thing, don't forget, is, here it is. That thing is a determinant. It's not a fraction. Right? So you can't just say, I'm just going to treat it like a fraction because, well, look, it looks like a fraction. Right? Therefore, it behaves like a fraction. That's not a fair argument. Okay, so let's ask, what happens if I do go the other way? What if I view u and v as being functions of x and y? Right? How would I do a pullback? What's the stretching factor? How much does this stretch area? Well, just, turn your head sideways. Or view this as seen from the back of the piece of paper, so whatever. U and V are the outputs, X and Y are the inputs, and our formula for stretching factor is Jacobian of the function that views the outputs, now U and V, in terms of the inputs, now X and Y. Right? So this is really the same formula, just with the variables playing different roles, but it's the same exact formula. And so having observed that, now let's take this formula for du dv, stick it into there, and what you find is that the product of these 2 seeming fractions is 1. Right? So plugging that into there tells you that this product is 1, and therefore these things that look like reciprocals of each other actually are reciprocals of each other. Isn't that nice? So the fact that this notation behaves like a fraction in terms of how this cancellation happens and how that apparent cancellation happens. It's kind of fraction-like in that sense. It's also fraction-like in this sense. So you can see why we like this notation for representing this with a notation that makes it look like a fraction, because it behaves a lot like a fraction in multiple ways. So let's write it as a fraction, as a sort of again a memory tool. So with that in mind, let's do this example, and I only have 30 seconds. Okay, I guess I don't have time. But anyway, let me just set this up. Suppose we have an integral defined on some domain in the xy plane, like this, as defined by these equations in the xy plane, giving these 4 curves. And how would I turn an integral on this domain that, again, look at the shape of this thing. It's got corners. No matter how you slice, it's got curvy edges. So this is a not good domain. How would I go about rewriting it as somehow being related to a domain that I like a rectangle? And it turns out that this is exactly the tool that we need to do that. And we'll pick up there next time. Okay, see you later. Have a good weekend, everybody.